Hi all, thanks all for coming. Today we have Adrian, prospective PhD student, RoboNotts team lead, here to speak to us about robots. So I'll hand off promptly to him.
Hello everyone, welcome to my talk. So you want a robot? Talk's been in the work for a while, so as Dowdy mentioned, I'm currently the team lead of RoboNotts and I'll be talking about them right at the end, but for now, let's get right into it. I'm hoping that this is recording, otherwise later it's going to be quite unfortunate. So, first of all, who am I? So I'm Adrian. I'm currently a fourth year computer science student. I'm team lead at RoboNotts, and my interests are in machine learning and robotic autonomy. I was also a HackNots 84 organizer. I'm sure plenty of you guys saw me there being quite silly. I hosted HNTV at HackNots as well. And, you know, I've just been around HackSoc for quite a while now. So, but most importantly for this task, as I said, I am right now a team lead of the RoboNotts robotic competition team here at UON. And I will talk quite a bit about them later. But let's have a general thought about this talk, a kind of why, a background. Why should we care about robotics? What do I mean by an autonomous robot? In fiction, robots are everywhere. Books, films, you know, cute little guys in WALL-E, the absolutely nightmarish thing from iRobot. I hate that thing. But robots are also present in real life right now. Many of you have devices and just things that are built by robots in factories. I'm from Milton Keynes. I know. And we have delivery robots that bring us our groceries. And a lot of you will have a Roomba hoover your floor. So we already have robots in our world, but I'm sure as all of you will know, the Roomba robots are beyond stupid. They can barely do corners, and they will somehow find the perfect route to bump into everything. So we want robots that can do complex tasks. We want robots that can clean for us, cook for us. Where are these? What are we missing? Why aren't our homes, hospitals, restaurants, shops filled with robots? And the problem is automation. It's really difficult. Dealing with environments that are constantly changing is really hard. And what's even harder is dealing with you guys, people. People are the worst and the bane of any decent roboticist. So, in all these examples, the main thing we're dealing with is a very high unpredictability. The more things we have in an environment that are moving, especially hospitals is a really good example, the more difficult it becomes to prepare for everything that could happen. So, with that in mind, let's have a think about how is this talk actually going to work? A little general overview. I am not an engineer, so this is not how to build a robot. This is the steps needed to automate a robot, basically. The most I know about hardware is that Dowdy is really good at blowing it up, but I will go over to some details in hardware when they're necessary. So what are we actually doing in this talk? So I'm going to give a problem, basically a robotic problem that was presented to us at a competition, and I'm going to break down how we solve that problem, all the different parts that we need to solve a really simple problem, and how we can get our robot of choice happy to complete it. So, that's not the right one. There you go. There's happy. You'll notice that the guy I have here is not happy. It's Bucky, a different robot. So I'm going to go over Happy a little bit first, and then I'll let Bucky introduce himself afterwards. Happy is our current competition platform for the RoboNotts team. And feel free to give him a little follow on Instagram. We're setting up his socials. He's got a picture up right now, but you know, more things are coming soon. The thing with Happy is that he's our own beloved little Frankenstein of a robot. You notice one of those pictures is a guy standing there in like full PPE. Happy used to be a disinfectant robot. So during the start of the COVID pandemic, lots of Chinese manufacturers built these disinfectant robots. They use really powerful UV lights. You drive them into a room, you turn the lights on, and in a couple seconds, all the bacteria is dead. And that's what the robot was meant to do. Meant to go in a room, disinfect it, go out. Few issues. If you were in the same room as it when it was on, your chance of getting cancer went up exponentially because those UV lamps are really, really bad for your skin. And second of all, the COVID pandemic ended. And everyone that was holding onto one of these robots just didn't really need it anymore. They're too clunky for hospitals. It's too slow. And you can't really reel it in with how big it is. Now, again, it's not here, sadly, but to give you an idea, Bucky's about a quarter of the size of Happy, and Happy weighs about 120 kilograms, so he's very big. So, what did we do? The lab, the CMS, more about them later, we stripped the lights off because we don't need them anymore. They're somewhere in the lab. And we built this platform on top of it, and we called it Happy. So everything you see in the picture above the base, so the base is manufactured by a Chinese company called Amy. Everything above here, we put on there and built. Obviously, the arms built by someone else as well. However, we do not have Happy today. So, Bucky, do you want to introduce yourself? He's taking his time. Okay. Go, fix. In the meantime, we'll continue. Yeah, God forbid. I promise you, so this is not our standard robot. I have spent the whole day getting this working for today's talk, and it manages to fail on the first thing. Okay, it's fine. We'll come back to it. So, let's talk a bit about the scenario. What is the problem we're looking at? Let's set the scene. You have just sat down on your sofa. You've got comfortable, you've switched your TV on, you've just put on your favorite computer file video, and then disaster strikes. You forgot the bowl of snacks that you meticulously prepared in the kitchen, and now you're gonna have to get up again. God damn it, to grab it. Who's been in this situation before? Be honest. Like, yeah. Okay, exactly. Now, I'm going to follow that question with how many of you have before imagined a world where instead of having to get up off the sofa, you could order a robot to do it for you. Now, I just use my little sister to do it, but that is the scenario. And, you know, the scenario kind of has a name. It's called the robot butler scenario. And the idea of this problem, it's a very common one. It's basically object delivery, something very basic problem. You know, as humans, quite easy. If I need to send Dali to go do something, he can do it very easily, like he just did just now. How is Bucky able to introduce himself? Wonderful. Please observe the Dowdy walk of shame. Well, let's break the problem down a bit. So we know our goal. We have a problem, and we need to task it with bringing us an item. Nice and simple, right? Now, to get Happy to do this for us, we need to break the problem down into all its composite parts. For those of you who did GCSE computer science, this is called decomposition. So, having a look at these points, I'm not going to go into ridiculous detail, but this should be quite straightforward. We find the person that needs the help, we go to them, we confirm what they want, we go to the location of that object, we find it, pick it up, take it back to the person, and give it to them. Nice and easy, right? So, once we've considered the what we need to do, we need to consider the how. So, here are just some of the questions that we need to answer about how we're doing these things. There are loads more points, and these are some of the ones we considered for the competition in London, the ICRA competition. That's what I'm going to be referring to it as for now. And you can see that the more you look into it, the more problems arise. How are we finding the person that's calling? How are we confirming the command? Are we using speech? Are we using a screen? Are we using an app? And things like picking the object up is really difficult. What if it's a soft object? What if it has liquid inside of it? We need to consider all these things, and once we've considered the how, we need to consider the dreaded what if. Because everything can go wrong. When it comes to solving problems of robots in real spaces, we lose the ability to abstract a problem, something that we're really used to as computer scientists. The thing that makes automation so tricky is we can't ignore problems, we can't make the problems simpler. Abstraction remains. And all of these problems in red are real. They have to be solved, otherwise our platform can't complete its task successfully. And these are just some questions that came up at first glance when I was making the slides. If you really start thinking about it, there are so many problems. And one, especially one of these, I'm not going to talk about them all, there's too many, but I'm going to talk about the last one. What if we fail? because we can't assume that a system is always going to succeed. A good system should be able to fail successfully, and that's something that we're going to talk about a lot at the end. So, there's one more huge concern, especially for us at RoboNotts, aside from all of this, and one that sadly is often forgotten when we talk about these technologies. What if the user is a disabled person? We want these technologies to help us, to make life easier for us. But if the user is deaf, blind, has a learning disability, some of those steps that I made up before, some of those questions, completely break. And our assumptions on how we're going to solve this problem become useless. Assistive technologies have to be accessible. These people are the ones that are set to gain the most from these kind of technologies. Now, the reason I'm mentioning this is because RoboNotts, the competition team, we are a part of the Cyber Physical Health and Assistive Robotics Technologies Research Group, mouthful. So this question is something we're always asking and something we're always trying to tackle in our methods. And I'm going to try and bring this up throughout the talk, but it's nice to keep it in mind how everything I say suddenly stops working when we try and consider a different user. So, I think we can, so that's a lot. There's a lot of things to consider. And I think one of the things I want to show you with this talk is that robotic autonomy is ridiculously difficult. And the closer we look at a problem, the closer we think we get at solving it, the more exponentially difficult it becomes. Luckily, we can test our robots in controlled environments, so we can focus on just some of the problems, not all of them, which is why this talk is only going to be an hour and a bit and not, a whole module. So, let's start by breaking down the problem. Can we have a maybe Bucky introduction first, actually? Let's give it a go.
Hi, I'm Bucky. I'm Happy's older brother, and I'm standing in for him today as he is currently exploded sad face. My aim this talk is to interrupt Adrian as much as possible.
Thank you, Bucky. It seems that Bucky's not got the right language package right now, so he cannot pronounce I'm, but that's its own thing. So, let's start breaking apart the problem. And you may have seen Bucky moving around here, and this is going to be the first thing to talk about. Navigation. How do we get from A to B? How can Happy make it from where it is to where it needs to be? And how does Happy know where it is at all? Interestingly, these are some problems we can solve together, and by choosing a starting position, calling it the origin, we can map out a region as we explore. And this is kind of similar to how you'd probably approach if I asked you to make a map of your room or your house. You'd get a tape measure and you start walking around and noting it down. So once we've got a nice map, we can actually start naming things. So foyer, living room, hall, kitchen, dining room, and so on. We can now add locations, we can add meaning to our map. Now, I mentioned measurements because it doesn't really help for us to approximate the maps. How are we taking measurements? Now, Happy also has one of these, so does Bucky. Bucky here, you'll notice there's a little device here which is supposed to be spinning, called a LiDAR. LiDAR is basically a ranging tool. The idea is that this device can tell us the distance from the center of the LiDAR to basically any point on this plane. So with that, we can find rules, we can find objects, and we can start to build up a map of the area. So you can see actually a good example in this picture here of the robot in the center, and the blue is what the LiDAR beams are reaching. I'm not going to explain how a LiDAR works. You can see that in this case, that robot only has a LiDAR that's facing forwards. This is actually the case for Happy. Happy's LiDAR is hidden away over there. It only sees forwards. This guy, his LiDAR has 360 vision, so he's actually quite a bit better at avoiding things. So, let's continue. Cool. With that, we can travel to the kitchen. The easiest way, what was that? Oh, I don't know if that was the robot or I'm imagining things. So we could just travel to the kitchen, right? Wonderful. Simplest thing we can do is just go in a straight line, right? I know where I am. I've got a map. I know where the kitchen is. Just go in a straight line, right? Sadly, corners. Sadly, objects. We can't go in a straight line all the time. So thankfully, people far, far smarter than me develop navigation algorithms, which can deal with unexpected obstacles as well, and I'll mention those a bit later. This lovely GIF I have up there is called Rapidly Exploring Random Trees. Not one we're using as part of the team, just one I think looks particularly cool. It would be an entire talk just to explain how it works and how it finds optimal paths. It's very cool. Now, another question is, wait, how do we actually move Happy, right? Because I'm being very computer scientist here, and I'm abstracting the fact that there are motors that we have to turn at certain amounts to get Happy to do things. Now, Happy has what we call a differential drive, modeled here. And we can use some lovely maths to work out how much we need to turn each wheel by to get it to follow the path that we've generated. Thankfully, as I said, some poor engineer has done the maths for me. And the maths is quite cool, but again, too much for this talk. And this is going to be a common occurrence of Adrian ignores kinematics and engineering as we go forwards. Now, I just skipped something, which is localization. How do we know where we are? And when do we update our map? So the object, first of all, let's talk a bit about obstacles. I'll get ahead of myself. If you've left your sock on the floor, we don't exactly want Bucky or Happy to slip on it. Worse, we don't want it to get stuck in the wheel and the motors. So the robot should be able to detect an obstacle and avoid it. And that's when we can use the LiDARs and the cameras to detect them. And suddenly we get a question, which is, when do we update this map that we've made? Right? We don't need to update the map, surely, if we find a sock, right? That's kind of a one-off occurrence. We're not going to say this area of the house is now a wall because there was a sock there. But maybe if we move a piece of furniture, maybe if we move a chair, maybe we do need to consider updating the map. And that's one of the extra questions, because there's no good answer to that. That is based on implementation. So lots of these open-ended questions to this talk. Now, another thing that we really need to know is how does the robot know where it is, right? If Bucky's made a map a month ago, I turn it off, and I put it somewhere else, and I turn it back on, how does it know where it is, right? It's just turned on. It had a map that was made earlier. How is it going to know where it is on the map? Now, this is a problem. It's called a self-localization problem. There's loads of methods to solve it. Here's my personal favorite on this GIF. It's called the Monte Carlo method. In essence, we throw a bunch of points at the map. We say, we are everywhere. And we move the robot, and we check every point, and we say, actually, are we there or not? And we remove the points, and we move them until all the points converge. You see, as the GIF loops, eventually all the points converge to where the robot actually is. But at the start, it assumes it is anywhere. Now, it's a really cool method. Unfortunately, this method is annoying because you have to move the robot to localize. So we actually have some other methods. April tags, so not QR tags. April tags are slightly different. These are very classic. If you guys have seen Boston Dynamics' Spot working, it uses the April tags a lot for localization. The idea is if we stick those tags everywhere in a building, a good option is the ceiling, because no one cares if there's something stuck to the ceiling, then we know where we are. Just find the tag, and we know we're there. And there's another option, which is a lot easier, and this is how a lot of your Hoover robots will work. Your Hoover robot always starts at the charging port, right? It's never starting from the middle of the house. It's always going to start at your charging port. So if the robot turns on and it is charging, we know where it is. So it's a much simpler, cleaner solution to this kind of problem, which is very well researched. I like looking at that GIF. It's a good one. So where have we made it? What have we done so far? Happy can now move around a space. And if we need it to go to a location like fridge or kitchen, we just need to make sure that we have those locations on our map. Now, just like that. So while he moves around, quick side note, that's a really fun use for machine learning. Automatically label locations and objects in a location. We'll talk a lot about machine learning later. But how can we move to something that's not on the map, right? So that bowl of snacks that you have on your table isn't going to be part of this map, this occupancy grid, we call it. So how are we going to move towards it? Now, because we have navigation algorithms, we only need to do one thing to get there. We need to approximate the location of the object. And then we can use our algorithms. But how are we going to do that? Well, we're going to need a pair of eyes. So, computer vision. So I've got Happy here, another picture of Happy. Happy is set with 2 cameras. Bucky over here if he wants to turn to the crowd, he only has one of the same kind of camera. So, as humans, we rely on our vision to gather information about an environment. Our robot is exactly the same. Computer vision can solve loads of our problems and our requirements. We need to detect people, we need to detect objects. And in more complex problems, we need to detect actions, movements, gestures. That's a whole other thing that I'll mention later. And how can we do this? Now, there are two big techniques to computer vision when it comes to robotics especially. Image processing, which is your more algorithmic, really fast, but very inconsistent. And sometimes you can trick these algorithms by just using a different lighting or using a slightly different shape of an object. And then the other option, the more popular option, machine learning. And we'll, again, lots of machine learning coming up later. But we can use, I don't know if have any of you heard of YOLO before? You only look once? No? No, you have? Excellent, fantastic. So YOLO is a machine learning model. In essence, it does object detection and not segmentation, and we'll get to that. Machine learning is technically really easy for a developer. You just need to throw enough pictures at it that it starts working pretty well. However, that's a lot of training data, and we'll get onto that in a minute. Now, it's worth noting those cameras, just before we move on, they are RGBD cameras. So that is a camera with 4 channels, red, blue, green, and depth. We can see how far away things are. This will be useful later. So, let's start by talking about person detection. We need to be able to reliably detect a person, otherwise everything breaks down, right? And detecting people was actually relatively easy for us. We used YOLO V8 model. I think we're actually on YOLO V11 now. YOLO V8 was the most up-to-date thing when we were in London. And it uses convolutional neural networks. And for my own sanity, I'm not going to explain that. Go do the ML module. All you need to know is that it takes a ridiculous amount of training data and lots of computing power. Thankfully for us, person detection is a really common issue, common problem. So we didn't train our own model, we ripped one off the internet because, again, this problem has been solved many times. However, YOLO is a detection model. Oh, I think there's a... YOLO is a detection model, not a segmentation model. Oops. What that means is that it...
You're annoying.
Yeah. That's fair. So the YOLO model only gives us basically a box around a person. I'll show you that in a minute. But what we want is to actually draw a line around a person. Because if I draw a box around me and you say, okay, to work out how far away I am, just take the average pixel, and this pixel is really, really far away on my corner, it's going to really skew the average. However, we can use segmentation to fix that. And for that, we use segment anything, and that is Meta, so Facebook model, which we give it the bounding boxes, and it gives us a lovely end result like this. So this is an actual picture from the competition. So you can see Happy in the bottom left corner, and our 2 participants sitting on the table, and you can see the result of YOLO V8 and segment everything. So these boxes here, produced by YOLO, and you can actually see the how confident the model is. So it thinks that this is 0.71%, 0.89, not percent, sorry. And then in orange is the segmentation. That is the actual shape that we draw around the person. That's given us by segment anything. And you'll notice something else, which is we have a lovely distance. That person is 1.62 meters away. And if you look here at the picture, it's not very clear, but from the camera to the person, almost 2 meters. So, with this, we can then go towards a person. We can see how far away we are. We need the distance, so the cameras help there. Now, that's the easy bit. What about other problems? Because this is quite a heuristic approach to person detection. There's some hard stuff, there's some problems, some extra things to think about. And these are things that weren't part of the task I said earlier, but some further steps that us as RoboNotts were currently working on. Sure, we can detect a person, but how do we know it's Dowdy? How can we tell it's him? If we're talking to someone new, how can we remember them? How can the robot understand who 2 different people are? And there's lots of different solutions to this. Facial landmarking, gait recognition is really interesting. And what if we see multiple people? If I've got these 3 guys sitting here and one of them calls to the robot, how do I know which one it was? How do I know which one I need to start talking to? Do I need to detect how their mouth moves? By sound? Maybe some stereo microphones? It's a tricky problem. And what if we want to follow someone, which is a really common problem in these competitions? How can we make sure that we're always following the same person? And now I'm going to go for an anecdote. The lab recently bought a new robot called a Temi robot. It's like kind of a guide robot, and it's really, really cool. It works really well. And you click it on the top, and it starts following you. But if someone crosses you like this, it'll stop following you and it'll start following them. That's not what you want, right? So it's, again, these problems come up over and over again when you least expect them. So, time for a little competition anecdote. Here's a picture from the ICRA event. And we have 2 users that we're interested in that green box. There are 2 problems in this scenario. Can anyone spot them? 2 issues. Feeling shy. Cool. So, we've got 2 issues. Firstly, the big wall between the robot and the people. That we solve by going around the wall. That's not the interesting thing here. The interesting thing here is there is a really big crowd of people in the back. We weren't expecting this when we got to the conference. We didn't think we'd have crowds of people with their cameras waving around and trying to take pictures of our robot working. And when we're running a model, it's going to detect all those people. All of them. So, how do we avoid detecting those people? Or how are we sure that the people we detect and we move towards are those in the competition space and not those in the crowd? How can we do that? And this kind of anecdote is a little bit of thinking on your feet and robotics competitions rather than robotics in general. There's actually a really simple solution to deal with the crowd. So here's what the robot can see from the last picture. So how do we deal with the crowd? Not in that way. We simply just ignore detections above the wall. So in the competition, you'll notice that there's actually, for those 2 people, there's Y values, Y213 and Y284. Because what we were doing is, if the center of that person was higher than halfway up the screen, they weren't a person anymore, okay? Is this lazy? Yes. Is this temporary? Yes. But that's a spirit of competition. For any of you guys have attended hackathons before, you will know what it means to be hacky and to make these solutions on the fly. And another thing to note is, this competition is supposed to simulate a house, but I'm sure that in your houses you guys don't have an out-of-bounds audience or crowd looking in. At least I hope you don't. So that's another bit of a competition anecdote. So that's person detection. We can detect people. That's great. Fantastic. What about object segmentation? I don't know why I use detection on one side and segmentation on the other. In this case, we are also using a CNN. Convolutional neural networks are really good at this problem. And why do we need to detect objects? Everything we do in the end is with an object. When we ask our robot butler to get the bowl from the kitchen, it needs to know what a bowl is, right? We can't say, go get a bowl, and it's just going to say, I don't know what a bowl is, right? So this is a really similar approach. We're using FCOS this time. So FCOS is a really interesting model made by a PhD student at the lab. I would love to explain it, but I read his paper and I didn't really understand it. So it's quite complicated. But the difference between this and the person detection is that we had to gather the data ourselves. So as a team, we took and labeled over 1,000 images. They're still saved somewhere. And unsurprisingly, that takes a really long time. So I think it's only Dowdy here that was in the team back then, but it was about 200 images per person, and that does literally consist of the picture on your screen, you grab your mouse, and you drag a box around every item that is of interest, right? So we ended up spending 2 weeks of development taking pictures of objects on the table and labeling them, and then we trained the model on the big, beefy GPU rack we have at the Cobot Makerspace, and there's the resulting model, which was just okay. And you can see everything it detected there, which it seems really good from this picture. But the reason it was really good here and not really good in the competition. Notably, you'll notice the background here is very different to all the pictures from London. That's because the model we built for the London competition overfitted ridiculously, because we were very naive. It was 3 a.m. in the hotel lobby in London when we got it working. And we started to get some decent numbers. We were like, okay, let's leave it to train overnight. Let's leave it to train overnight. But we won't tell it to save every model, because if we do that, we're going to run out of hard disk space. So we're only going to save the most recent model. Excellent. We wake up in the morning, and Daddy's laughing, because it was literally the first thing I did. I called him in the morning, and I said, check the model, check the model, check the model, right? He checked it, and if you guys have seen what a confidence matrix is before, perfect one. 100% classification accuracy. For those of you that have trained machine learning models, that sounds really good. It is the worst. It means that your model is not going to work on any new objects. And that means that we actually spent most of the London competition without any kind of model. And we had to revert back to this old one from an older competition. Again, these competition anecdotes are going to come back a lot, because we were lucky. Some of the objects in the competition were the same as in this older competition. So we were able to use this model. However, this model was really terrible at London. And I mentioned backgrounds. We took all of those 1,000 images, were all taken in the same room, on the same table, with the same objects. Again, those of you doing machine learning that might have worked with these kind of models before will know that's a big no-no, because the model is going to learn what isn't a background rather than what is object. So the model actually performed very poorly the second you put it in a different background. So, anecdotes. So there are other methods to object segmentation, landmarking. There's also SIFT, which is interesting. I've not really explored them, but it's something we want to look at. Quick shout out to Jiling, PhD student, not here, but he is the one who lent us his really fancy model, and his model was designed to deal with obstructed objects. So you'll notice there's actually a tiny little medicine bottle there, which it's managed to detect behind the bowl. And you'll notice that a lot of these models, they sometimes do very poorly when more than half of the object is obstructed. So we have that. We have movement. So we should be able to move towards something, right? So how are we going to do this? So this is a real step-by-step. This is kind of the thing that I implemented for the competition. And the first thing I need to mention, which I kind of skipped earlier, is what is odometry. So odometry is the ace up our sleeve. We can actually approximate where the robot is by how its motors have turned. So there's 3 layers. There's where we want the robot to be, where it is, and then where we think it is. So you can imagine the longer the robot runs for, the bigger those get separated, but that's its own issue. So it's kind of like working backwards from your movements. If I tell you to take 5 steps forwards, 2 left, you will kind of know where you are based on your own stride, right? So we can cross-reference this where we think we are on the map, take the difference, and find what we call a transform. Really fun. No. And that also gives us the facing direction of the robot. We can figure out how much we've turned over the entire time it's been on. So we know the position of the robot. We know where it's facing. We know how far away we are from a person. So we can work out where the person is. So I skipped it. Whoopsies. Some really basic trigonometry incoming. So we have a robot H for happy. Not happy right now. And an object O in a triangle, which I now realize is like an Illuminati logo, which was not done on purpose. So how can we figure out, if we're happy, how can we figure out where that object is so we can move towards it? Because we need to know its X and Y before we can get to it. So first of all, some really obvious measurements. I drew this at like 1 a.m., so if you guys can't understand my handwriting, I'm sorry. We have X and Y of happy. We have our OX and OY, which is our objects, X and Y. And then we have our DX and DY, which are the differences between the happy and the object. And that's what we want to find out. We want to know how far away it is in DX, how far away it is in DY, so we can get there. We also get a theta, which is the angle the happy is facing, and that is relative to where the robot started. So I'm using that line as 0, because that's the line we commonly use as 0 in robotics. I'm not sure about engineering or whatnot. And then we have our distance d, which the camera gives us. So we need the odometry, right? That's the odometry. That's what the robot says. I say, robot, where are you? Robot says, that's my position, and that's my rotation. Hey, wait a minute. Why is there 4 numbers in the rotation? I think I heard someone say quaternions. You're absolutely right. So for those of you who don't know what quaternions are, good. So 4-dimensional numbers to describe 3D rotations. Really fun stuff. Turns out it makes it really easy to do some conversions and avoids a thing called gimbal lock. Really fun. I'm a computer scientist, not an engineer. I'm not trained to be teaching this. But we don't care about the quaternion. We just want the rotation of the robot. Now, there's 3 dimensions. So you can turn this way. That robot isn't doing that. You can turn this way. That robot isn't doing that. Or you can turn this way, which is the only one we care about. So once we transform that from a quaternion into roll, pitch, and yaw, we get some angles. Now, it's not turned in R and not turned in P, because if that was the case, the robot would have tipped over and we'd have a bigger issue. But we have a nice yaw, which is minus pi over 4. This is a really terrible choice for a number for this example, and you'll see why. So we have this rotation. So with that rotation and the distance that our camera gives us, I'm using the distance from that picture we had earlier, we can find dx and dy. I'm sure everyone here knows trigonometry. You'll see why it was a really poor choice, because it turns out that pi over 4 is 45 degrees, so we're going to get the same dx and dy. So we have the change in x, we have the change in y, we work out where the object is. Nice and simple. This is the only maths I'm going to do for this talk, I promise. It's the only maths I'm qualified to do. So we have the position of the object, so now we can say to our algorithm, can you please go to 1.9, 2.2? Okay? Now, quick side note, if you say that, you're going to go into the object. So it's always worth to actually tone that distance down a bit so we stop in front of it. And this method is actually very effective, and it works very well with our SLAM algorithms that do the hard work of avoiding objects and finding our path. So, where are we so far? Again, happy can now move, happy can now see. We've covered 2 of the biggest things that we need to complete any of this butler task. However, I've skipped something that's really important and we needed well before moving and well before seeing. I'm sure some of you are already wondering what it is, and that is human-robot interaction, communication. Our robot butler would be pretty useless if we can't tell it what we need, and if it can't tell us what it needs. So human-robot interaction is all about how our robot interacts with humans in any way, and that's not just via the voice. To figure out what we need to think about, we're going to have to look at good human interaction. So talking when it's your turn, listening carefully, correct and meaningful replies. If someone says something to you and you reply in absolute gibberish, they're going to give you a weird look, or call an ambulance. We want to be respectful. Body language is something that we sometimes forget as humans, which also applies to robot. Body language and appearance is actually very important for robots. A little anecdote from my time working with robots. Some people are absolutely terrified of Spot, the Boston Dynamics dog. They think it's creepy. They don't like it. Other people think it's really cute because robot doggy, right? So appearance and body language is actually really important in this field, especially if we want these things to be in hospitals. We can't build a robot that scares children away, as fun as that would be. So facial features also apply here. Currently, Happy nor Bucky has a screen. Used to have a screen. We tore it off. But another thing is, if we have the ability to display a face or something akin to a face to a user, we should use that opportunity. And also, how do we let someone know we didn't understand them? I'm sure when you're in conversation with someone, it is kind of annoying to go, what? I know that from first hand because I'm very deaf. So once we've considered what it's the good things to interact with a person, we can start thinking about all the different ways we can communicate. I promise I'm not going to go all over this. This is just information. So we know it's not just what Happy says, but also how it appears, how close it gets to a person. All of these things that need to be considered if we want to make sure that the user is comfortable using the robot. Now, we have a few choices. Classic verbal communication, just like we do with other humans. I'm sure a lot of you have smart devices at home. I know that in our house we have a Google Home in every room. And there are some scenarios where this is tricky. And another good option is for our robot to have a screen or a companion app. Sometimes it's forgotten a lot in roboticists trying to make it really robust communication system when everyone has one of these in their pocket, which makes for a really easy remote. However, ends up not being as natural as speaking, especially if you're sitting on your sofa and maybe the phone is the thing you want the robot to get. You can't use it, right? So sometimes we want to also consider the unexpected, right? A great way to figure out new features or requirements is to actually make a note of when someone says something and we don't understand it, right? I know in my house, the words, "Okay, Google, set a time of 15 minutes," is basically said every day, right? So there are some other fun considerations when it comes to HRI. You'll notice that haptics, that is having motors on your body that vibrate. That's what I'm doing for my dissertation. If anyone's curious about that, come have a word with me at the end of the talk. And gestures as well. Gestures are a really curious one. If a user is mute or deaf, maybe want to communicate in sign language or some sort of gesture system. Okay? But today, we're going to focus on voice interaction because that's the problem we were working on. Okay? So we're going to look at the HRI implementation that I built for the ICRA event in London. Oh, actually, we're going to watch how it works first. I completely forgot about that. So I'm going to try and get this video working. So if you give me a quick second.
How may I assist? I'm looking for you. Hello, how can I help you today? Please speak clearly. Alright, would you like me to get the tomato_soup_ come from the shelves?
Yeah. Yes. Yes, please.
Could you please go over that again? I didn't get it.
Drink the soup can from the
Apologies, I didn't understand. Can you please repeat it?
Can you please bring us the soup can from the living room?
Please stop. Okay, let's talk about that for a second. So, what did we want to happen? We have this process. We prompt the user to speak, we listen to the user, we process the speech, we determine what the user wants, we repeat it back to the user, ask them to confirm it, and then do it. Quite a few things went wrong in that video, as you might have noticed. First of all, the funny one where it goes tomato_soup_can. That's actually a bug in my code where, so every object had what we call a technical name, so with all the underscores, it's what we use in the code, it's always consistent, and then a lovely semantic name, so when the robot speaks it, it sounds nice. I accidentally flipped the variables around. So when it was doing the technical stuff, it'd use soup, and when it was speaking, it would do that. And you'll notice how, I'm going to show a clip again later, we fixed that during the competition. Another issue, the robot listened to the person and understood her perfectly. Do you want to get the can of soup from the reading room? Obviously, mispronounced and with underscores, but it understood it. And then it did nothing. And then it did nothing. And the users kind of look behind them, they're not sure what to do. And then the robot starts again. Why? We got stuck on the repeat this back to the user. We're expecting them to go, yes, that's correct. The users didn't do that though. So that's another thing where sometimes the user, you think they're going to do a certain thing, but they don't, right? And we'll talk about a few other funny things that come up with speech recognition and just interacting with a person. Now, my implementation, so what I built, came to be known as Bocelli/Andrea. Absolutely terrible name, Dowdy's fault. And these are the steps that Happy followed in that clip. And how do we do this? So how do we follow these steps? We're going to have a quick look at the implementation. Not going to go into the maths of natural language processing, because I'd rather shoot myself. But we can have a look at everything that we used. So this is actually, I stole this diagram from the paper that we had to submit for the competition. So this looks really complicated. There's not that much going on. We have 3 basic steps. Speech to text, to understand what the person is saying. the natural language understanding. So that is not NLP, slightly different, processing natural language, which is understanding. We want to take what the person said and figure out what is that they actually want. And once we figure that out, we actually need to generate the action, an action generation. And this loop, this cycle, is actually something that's being worked on really hard right now by lots of researchers and big companies, and I'll mention all of that at the end. And the way it works is very simple. You say something, I get that in text by using text-to-speech. So that's using Google Cloud Speech and Sphinx, because I'm not implementing that myself, no thanks. And then we have this natural language understanding, and this is the interesting part, and I'm sure a lot of you are seeing this and going, oh, he used an LLM. So the first part of taking that data is actually to break it down. When you say, can you please bring me the bowl from the kitchen, only 2 of those words matter. Bowl, kitchen. Everything else, I don't care, right? The point of this dialogue flow system, and I won't go into details how it works, but whenever you get an automated call, and it's not a human, and it's the most annoying thing on earth, and it's really obvious, likely waiting for you to say something, and it takes you down a path, and then you accidentally hang up, and you have to do it all again, that's using dialogue flow. In essence, what it does is it takes text of what someone said and tries to infer something from it by a training. So in this case, we trained the action of saying, can you please get me object from location? Dialogflow's job is to find that object and location no matter how you say it, and we'll talk about that in a second. And then ChatGPT actually had 2 uses in this case, which I realize it's not actually noted. The first use was as a failsafe. If Dialogflow fails, which it does often, we can actually just use an LLM to try and figure it out for us. It's less robust, and it can go wrong a lot, because if you solely rely on an LLM, here's what happens. Hey, Happy, can you bring me can you bring me a can of Pringles from the kitchen? As an AI model, I am unable to, so we don't want it to do that, right? So, and lastly, good old textual analysis. That's a fancy word for saying if the word bowl appears in the string, proceed. Thankfully, we did not have to use that too much. And then action generation. And that's where a lot of research is happening now. How do we go from bowl kitchen to actually the robot needs to move to the kitchen, find the bowl, pick up the bowl, take it back? How do we actually structure all those robotic actions from a single sentence from a person? And obviously the other option is, if that action doesn't make sense, we ask them to clarify it. And the way we actually confirm it back to the person is through ChatGPT again. So this is a bit of research that we kind of did by accident, which was we found that using ChatGPT to produce what the robot says to the person is really good. Because if the robot says exactly the same thing to you over and over, every single time, you start to hate the robot. You want to punch it in the face for not understanding you. But if the robot has a different message every time, and it's kind to you, maybe it's even a little funny when it doesn't understand you, then you kind of acclimate to it, and you don't get mad at it anymore. You're like, oh, it's just a silly little robot, you know? I'm sure a lot of you, especially our Google Home, when it hits us with the, sorry, I didn't quite get that, it's like I want to, you know, punch it off the table. So that's a very good use for ChatGPT. Oh God, my battery's running low. Dowdy, I need a cable ASAP. Quick intermission. Well, that's you're really going very fast there, Dowdy. I'm on 1%. I don't know why my laptop did this to me. Most prepared computer science talk. This is more like a hacksock talk. There you go. There's a plug here.
There's a plug here.
Oh, okay, sure. Thank you, Dowdy. Quick.
That's cool.
That's it.
It makes electrical noises.
Oh yeah, this plug is a fire hazard. This plug is famous for being a fire hazard. Actually, funny anecdote about the competition. I completely forgot. I was banned from taking this into the competition at London because of high risk of explosion and fire. I brought it in anyway. I didn't have another cable. No one stopped me. So, this system is fantastic, great, you know, Bocelli, Andrea, Adrian, you've done such a good job. Why don't you publish it? Because it's not robust, right? How many different ways can we say, could you please bring me the cup from the living room? I'm not going to read them all out, but you can have a read. There are so many different ways. First of all, synonyms. Someone might say mug instead of cup. Someone might say sitting room instead of reading room, which is what they called it, the competition. That sounds really weird to us, but it's because the guys who made the competition were German, and I'm not sure if anyone here speaks German, but apparently the living room is reading room in German. Not sure about that. What about different tones? Here, I'm assuming the person's really kind, but what if I just go, bring me the bowl from the living room? We need to be able to detect that as well. Unexpected concepts. If we want the person to grab a mug and actually say, oh, could you please grab my tea? How does the robot know that when you say my tea, it means a mug? And second of all, when it gets to the mugs, how does it know which one has the tea in it? That's another thing. Different command order, flipping it around. Can you go to the living room and fetch the cup for me? That should still be detectable. And lastly, missing context. Can you please get the cup from over there? How the hell does the robot know what over there is when I do that, right? You know, gestures, there's lots of fun ways of doing it, but I'm not going to go into that. So all of these things happened in the competition, right? The user is only told the object and the location, and it's up to them to think of how they want to say it. So all of these happened, right? So this is something that we need to consider, and they're there because all of these failed in our case. We did fix it. Synonyms are fixed by Dialogflow, and the order is fixed by ChatGPT. But the point still stands. The more we think about real life, the more difficult these tasks become. Almost there, right? Speech is really important. With that covered, we can do everything but the actual task, right? We've done everything except picking it up. So we need to pick up the object and take it to the person. And here's the part where I embarrassingly say that I suck. Because here's the part I've been avoiding, manipulation. Manipulation, all about grasping, moving, and carrying objects. It's really hard. The mathematics, kinematics, behind using robotic arms is really complex. It's far more complex than the maths I showed in the navigation. And it's the part of robotics that I'm actually least familiar with. So I'm not going to go into a huge detail of how manipulation works at all. And it's one of the aspects that we as a team are currently working on getting down solidly. And later I'll show you a clip of Happy completing the task, and you'll be like, wait a minute, Adrian, that arm is moving in that video, you lied to me. We controlled it with a mouse and keyboard. Because you're allowed to do that in a competition. You can say, yep, we're going to control the arm manually. You can only get half points for doing that, but it's more than 0 points. So, as I said, we're really hard at work on trying to understand manipulation. It's one of the reasons why we need engineers, because kinematics is hell. And I really don't want to look at any more kinematic-like drawings of arms. So I'm going to leave that there. Now, Bucky here does have an arm. Can I get a rotation? Can I get a 180? There you go, thank you. I wish I could show you Happy and his arm, because his arm is far cooler. But here, Bucky has an arm with very simple joints. It has a shoulder joint, rotates like this. Then it has, oh God, I've forgotten the name of the joints. But you can see 1, 2, 3, 4, 5, 6 degrees of freedom. So if you imagine that I want to grab this object, and there are 6 different things that I can turn, and I want to get to a single point on this object, it becomes hell to do that maths. Especially if the object is really weird, like the microphone. I need to grab it like this. If I don't grab it like this, I'm not grabbing it. I can't, this isn't going to work, right? How do we know that? How does the robot figure that out? And that's a big point of research. There's quite a few people in the Cobot Makerspace lab that are working on research like that. And that's it, right? No, there's one thing left, one more thing left. Our robot has all the skills it needs to complete the task, but there's one thing that I haven't mentioned really. How do we put everything together? We've made all these separate pieces, all these different bits of software, some bits of hardware, and they're all working individually, but how are we getting them to work all together? Because in the end, that's kind of the most important thing, and this is what I called orchestration. And that's kind of, how do we put everything together? Do we just implement a procedural program that just goes like this and hope everything goes perfectly and we don't have to restart? Or maybe some sort of lovely state machine. Now, we're using the ROS, known as the Robotics Operating System. Has anyone here used it before? Excellent. So you guys won't know how much of a hell it is. It's quite tricky. It allows us to control all the aspects of the robot in what's called a subpub system. So each different piece of this robot is publishing what it's seeing or what it's doing, and we can then publish to it what we're seeing or what we're doing. So for example, if I say to it, I want you to turn around in 360 degrees, I go to the base and I say, hey base, here's a message, turn 360 degrees. Thank you. Awesome. So, ROS is a massively steep learning curve. We're currently as a team, we're using ROS 1 right now because of limitations with Happy, but we're moving to ROS 2, which is supposedly slightly easier. And honestly, ROS is kind of the biggest barrier when it comes to people getting into robotics. in education, especially because it's very difficult to set up, not just for us as computer scientists, as roboticists, but especially for in engineering. And I know the Formula student guys also been suffering with ROS. So what I did, we used ROS, and then we have one large piece of code known as...
Skill issue, honestly.
Thank you. So we have one large piece of code that's called the orchestrator. And that's what brings everything together in a state machine style kind of system. And it works quite well for these kind of tasks, very simple task. It is a step-by-step task where at each point we can fail. So we go to a failure node and we can manage it. We can draw it in a nice little diagram for those of you that have done LAC. You know what a state machine is. This works really well for these kind of systems, but the second you have a robot that needs to do multiple different tasks in multiple different ways, maybe in multiple different places, it starts to break down. That's where machine learning comes in, but we'll talk about that later. So, we've got it all together. Let's watch Happy one more time do the task in full. If I can get the video up. So, one thing before I play this, you will notice that the speaking in this, the robot speaking in this version is very rudimentary compared to the earlier clip. That is because the competition was over 3 days, and this is the first day's worth of stuff. This was the 4 to 5 hour hotel lobby programming nightmare. And that's when the robot learned to speak like a normal person, like a human being, and speak nicely. In this case, you'll see how kind of hard it is at talking and how annoying it is. And there's another little anecdote. One of these guys is Swiss. He has a very thick accent. What happens? The robot doesn't understand him. That's another thing we need to consider that I forgot to mention.
Hello, how can I help you today?
Should we just go again? Can you bring the Windex bottle from the reading?
Repeat that for me, please.
Can you bring me the Windex bottle from the reading?
Repeat that for me, please. Repeat that for me, please.
Bring the Windex bottle from the reading.
All right, I will fetch the Windex from the reading room. The Windex.
few tense moments, Happy has managed to pick up the Windex bottom. Please note there is some teleoperation assisting the autonomous modules here.
He didn't let the crowd think that we did that autonomously, which is really sad. But yes, if anyone actually wants to watch the whole video later, I can give you a link. It has our section and the two other teams that completed the task. So, back to my talk. And with that all completed, that's it. Kinda. I say kinda for a reason we'll get to in a second. 1 second. Oh, my laptop is acting up. So, putting everything together, we did actually win the competition. We took home gold. But this doesn't mean we're anywhere near done. You saw all the errors that were happening there. You've heard all the problems that happen that I've mentioned over the course of this talk, and problems that we haven't solved yet as a team. And more competitions are within our sights, and our team is working really hard. And that's, so me, Dowdy, and Jiling, along with Simon and Dominic, they're lab technicians, and Praminda from the head of the research group. Now, I'm going to quickly mention, so this is kind of now aside from the talk, student robotic opportunities here at University of Nottingham. So right now, sadly, the only opportunity we have as students to participate in these kind of robotics is the RoboNotts team, which has only existed for 2 years, and I've been in charge of it for the 2 years it's existed. So we're looking at participating, so the main team, it's technically an at-home team, we don't really say it though, because we participate in robotics in the home. Those are the kind of things we do. And we're currently looking for engineers because it turns out that most competitions want your robot to not look Frankensteinian, really dangerous. So that's why we need mechanical engineers, and we need electrical engineers because the battery blew up twice. That's why I have this and not the actual robot. However, in the future, we're looking into opening up student opportunities for robotics in the school, in both faculties, in all the faculty of science, sorry. And we're looking into opening new teams. So we want a search and rescue team. For those of you who don't know what that is usually with dog robots like Boston Dynamics Spot, and that is basically going over unexpected terrain and finding victims. Robotic football, very self-explanatory, very fun. Formula 1/10, really cool. 1/10 scale Formula 1 car that's fully autonomous, and they race head to head. I don't know why I didn't take a video, but they were there at ICRA. It was really cool. And unlike, so Formula Student does autonomous racing, but that's time trials. It's just who can do the lap the fastest. Whereas in Formula 1/10, you actually race against someone else. So you suddenly need AI to overtake, to figure out when to close and open a DRS flap, and so on. It's very cool. We want to open a secondary learners team, especially for those of you in first and second years. Again, not just in School of Computer Science, in all the schools. We want to open robotics up at UON. And lastly, we want to make our own competitions here. The UK scene for robotics right now could be doing better, let's say. And we want to start it back up again, especially here. We want to start competitions with nearby universities. And these are the kind of stuff that I'm currently working really hard with the school. So if any of you have any sort of interest in robotics whatsoever, please scan this QR code for me. The QR code here, well, I'll bring it up again at the end of the talk, but the QR code here is just going to ask you some basic questions about your interest in robotics. The reason is that we want to show this to the faculty, show this to school and say, look how much interest there is in robotics. Can we please have more, right? For those of you, most of you are probably here from CS. We have one module in 4th year. By the time you get to 4th year, you already know what you're interested in. You're not going to take a really difficult robotics module. Who here has actually taken that ARS module? Wow. Just me and Dowdy then, I guess. It's a tricky module, but that's what I mean. We want robotic opportunities earlier, and we want to do more things with robots. So yeah, please scan that code for me if you're interested in robotics. It basically just signs you up to a newsletter for now, because we will be looking at getting people to participate in all these lovely things that are coming up starting next year, hopefully. Now, one last thing before I end the talk, which is, I mentioned it a lot, actually, is this. Machine learning and AI. Adrian, you really didn't mention them. You mentioned them a lot, but not in much detail. That's because it's a really, really hot topic of research. It's what big companies are up to. Machine learning is currently solving lots of those problems that I've mentioned, or lots of those problems that I've mentioned throughout the talk can be solved with machine learning applications. Tools like transformers, imitation learning, recurrence learning are really paving the way right now when it comes to robotics. And I've got some lovely examples here. These examples are actually all from the Google Research, Meta Research, and Boston Dynamics research pages. You can actually read these papers. They're very interesting. And a lot of them are actually about, if a person says something to you, how can you immediately turn that into what a robot does? Without going through, you know that whole talk I just did about all the different things you have to do this one task? What if we had a machine learning algorithm that did all of that for us, that can figure out the navigation, can figure out the manipulation by itself? And lots of very interesting papers. I've got some lovely examples here. Top one is probably one that you probably haven't seen. That's Palmy. That is Google's robot for research. This one's really cool because you can tell it to go pick something up that it's never seen before, and it will find it and it will pick it up. Google has a lot of data to help it do that. You see a Boston Dynamics spot here, but that's from Meta's research, and that's actually Meta's way of solving the problem that we did today, all using machine learning, the entire thing, right? Very interesting paper. And obviously Atlas from Boston Dynamics. Now Boston Dynamics is a kind of special case here because they're not really looking into the research of autonomy. They're more about the actual engineering part, but they're very, very impressive. I'm sure everyone's seen the videos of them dancing. If anyone has come to the lab when I'm working on my dissertation project and I've got Spot with me, it's an absolute pleasure to dance around with it. So I wanted to mention that because this is kind of the route that robotics is taking right now. And I know there's a lot of computer scientists that have lots of interest in machine learning. That, I love machine learning. I think it's really cool. And they don't really know what to apply it to, though. They have this interest because it's really popular, but then they don't actually know how to decide what to use it in, right? And robotics is a big thing that's coming up. And I think a lot of people will agree that robotics is the future and we're all going to have home robots and whatnot. And this is the way forwards. And that's why I kind of wanted to mention it. And with that said, thank you for attending my talk. If there's any questions, feel free to put your hand up or to just come here and chat with me. Thank you to Nishi and Eva from the robotics team for doing our best to get work with a robot that we've not used before. So yes, thank you very much.